So let's have a look at problem 17.1 now. Here you see a feedback loop with two transfer functions given to us. This is a second order transfer function. Let's call this G1, and that's a first order transfer function. Let's call this G2. Now this loop can be equivalently represented in this form here. This is the controller K, that's our G, which is given here. So let me use some color notation, G, and then we have GD, which is given here. So you can check that the same loop is equivalent to this loop here, where we have inputs R, this is negative feedback, and this is input D. And then let's just name the signals. That's Y, that would be U, that would be E. Now what we observe here is that the controller receives error signal, and this error could be due to either the reference input or due to a disturbance going through GD. So it is important to note that the controller does not receive the reference signal separately or the disturbance signal separately. So all it has is the error, and it has to recognize whether this error is from the reference or from the disturbance, and this will be important later. So this is the structure. Now let's look at the control goals. So the control requirements or goals for this problem are: first, we consider step response. So we consider step inputs at the reference. So step at the reference, and the first requirement is that the rise time is less than 0.3 seconds, and the second requirement is that the overshoot has to be less than 5%. So that's this requirement here, the tracking goals. Then we have a step at a disturbance T, and the disturbance rejection requirements are that the output Y should belong to -1 and 1 for all times, or let's say for all t. And then the second requirement is that is the settling time requirement. So the output Y of t must be between -0.1 to 0.1 for all times greater than 3. So this is the settling time requirement. And then we have a third input saturation requirement. So the control input u of t must be between -1 and 1 for all times. So this is the tracking objectives. These are the input disturbance, rejection objectives, and this is the input saturation or input constraints. Now the whole point of this exercise is to see the trade-off between good tracking performance and good input disturbance rejection performance. So let's see how to do this. So what we know is that if we write the problem in the form of an H-infinity optimal control problem with the help of a generalized plant, we can use the Hinf command to find the controller that optimizes this H-infinity norm. So let's write the structure of the problem. So we have some input R, output Z, input U, output Y, and we are looking for a controller K. Then if we write this, so let me just bring this further. If we write this block as T, which is the closed loop, and that depends on the controller K, then the problem of finding a controller K that minimizes the H-infinity norm over all stabilizing case can be solved by using the Hinf command in MATLAB. So this is what we will use. So this will be our key tool to try and solve this problem. So as a first step, it is recommended to use a two-block design, or in other words, to minimize the H-infinity norm of Ws times S and Wk times Ks. So that's given in the hint. So that leads to a two-block structure, a generalized plant. So let's see how that looks like. So it's called two-block design mainly because this closed loop plant is a 2x1 block system, and let's see how the generalized plant looks like in this case. So we don't need that one. We have the error E, and so this is our usual block that we have seen before, and now the transfer function from R to E is Ws, is S, and then if we pass the error through ws, we get ws times s. And similarly, if we take a block wk, take this out, so that will be t of k. So we are looking for a k that minimizes this. Now you can see clearly that we have r e here, so that one would be ws times e, and that one would be wk times u. So if r is the input and wse is the output, this is nothing but, so t of k for a given controller is nothing but ws. So r to e transfer function is the sensitivity, and e to wse is just ws times sensitivity. Similarly, r to u is the control sensitivity, that is k times s, and u to wk times u would then just multiply by wk to get this. Note that these are clearly depending on the controller k. So we want to find a k that minimizes the h2 norm of this block. So that is z1 and z2, and then we do have indeed that ws times s and wk times ks times r would be z1 and z2, as we have here. So now we can write down the generalized plant as follows. So now the same loop, now I will just move the k down, so that's still our g. The output of g is y, so that would be r, this would be e, so then we would have a k block below that we want to find. This would be u, this would be the performance channel set, and the controller measures the error e, so that goes to the controller. E. So now we can draw a block around this guy. So this would be our G generalized plant, and its inputs are R and U. That would be E, that goes to the controller. That would be the output channel Z. So that's our generalized plant, and we look for a K that minimizes the closed loop norm. So once WS and WK have been defined, this generalized plant can be constructed in MATLAB using this code. So that's a section of the code that you see. and this is exactly the generalized plant that we just saw. We have to define the system names GWS and WK. The inputs R and U, the outputs WK, WS, and the error R minus G. And so this is basically the syntax, and then you execute this command, and that gives us this generalized plant. Then once we have the generalized plant, we can execute this command to get the optimal controller K. So you've used this before, so I think you should be familiar with this by now. So that's the setup, and then we can design different shaping filters in order to have the corresponding tracking performance. So for example, a standard shape of a shaping filter WS would look something like this, and then the inverse of, so this is the frequency axis, and this is WS of J omega magnitude, and then the inverse, if you also plot it in the same figure, looks something like this. And the way to think about these shaping filters is to sort of put a weight on the different frequency ranges of the sensitivity plot. So for example, if you want to, so let me just bring that back again. So this one is the inverse shaping filter. So let me remove the actual one. Let's just look at the inverse shaping filter. So we can then use the shaping filter to sort of push or relax weights on different frequency ranges. So if you would want to push the sensitivity down here, you would increase the weight on the shaping filter WS, and therefore the inverse would go down further, in some sense trying to push the sensitivity down and allowing it to be accumulated here in some senses. So that's how you look at the shaping filters. Now, in order to satisfy the requirements for part A, it's quite straightforward, and I leave it to you to do that. Satisfied. So part A, let's quickly go. Part A requires the design when this thing is 0.05, whereas part B, let me bring part B first. So part B now requires to do the same design with a gain of 0.5 here, so 10 times the disturbance. And now I will discuss part B. So because with the gain 0.05, all these requirements are quite easily achieved, and you can just try this, and if you are stuck, please let me know. Let's talk about part B. So let's look at part B now. Part B requires now to change the gain in front of the disturbance from 0.05 to 0.5. Yes, or in other words, now we have 10 times the disturbance. So for these requirements I should say that the design, it seems impossible to find a controller that achieves all the control objectives. So what I want to discuss now is two things. One is the 4-block design, which we should use for designing the controller for this harder problem, and I want to discuss why this problem is hard, or in other words, nail down why it seems impossible to find a controller that achieves both the tracking objectives and the input disturbance rejection objectives while maintaining the input constraints at the same time. And then we should check, can we solve an easier problem. So this is what I want to discuss now. So let's first discuss the 4-block design. In the previous subproblem to task A, a 2-block design was enough. In the 2-block design we had such a closed loop transfer function, and then we found a controller that minimized the h infinity norm of this one. Now for a 4-block design we consider explicitly the disturbance. So we have two inputs and two outputs, and that is why we call it a 4-block design, because we now have 4 different transfer functions that define the closed loop system. So let's see how the 4-block design generalized plant looks like. So coming back to the original problem, now we have not just a G but a GD. So let me just bring this down slightly. Coming from the disturbance D. So let me just have the disturbance here, and this one is Y, that's R, and this is E. Now we have two inputs, R and D, and the two outputs now for this design are still the same. So we take E, pass it through the shaping filter WS, and call that one the first output Z1. Then we take the U, and pass it through WK, and call this one Z2. So now if we draw a block around here, we would have two inputs and two outputs, and this is exactly what we see here. So now let's just write down these transfer functions. So we have from R to E, the transfer function is just W is just S, and from E to Z1 is WS times S, so that would just be WS times S. Similarly, from R to U we have as before WK times KS. So this was already there in the two block design. Now we have two more blocks, which is because we have an additional disturbance input, and this is from D. So let's see what's the transfer function from D to E. So let's call this one the D after passing through GD D1. Now let's calculate the transfer function from D1 to E. So what do we have? We have E is equal to D1, so that is E, so minus E, rather minus E, because of this minus sign, minus E is equal to T1 plus GKE. So we would have D1 is equal to I plus GKE, or in other words I plus GK inverse D is equal to E, and this guy is usually called the input complement input sensitivity. We can call it either SI or SD because it's the sensitivity at the disturbance. So that's the transfer function from D. Oh, sorry, this was from D1. So I started with D1. I should stick with D1. And now from D to D1 is just GD. So we would have then I plus GK inverse GD times D is equal to E. And let's then call the first one SD. So we have SD times GD times T is equal to E. But now that is up to E, but then the signal E is passing through WS. So we have finally WS times ST times GD. That's this transfer function. Now to U we have up to E SD times GD. To U would be K times SD times GD, and then WK. So that would be WK. So let me just make the box bigger and also write this one again. So we have WS times ST times GD and WK times K times ST times GD. So that is the 4-block design. Now what is usually done is that we add additional blocks, filter blocks at the input of D, which we call VD, and at the input of R, which we call VR. So then we would have here VR and VD, R and D. In fact, we could also write this, we could pull out the WS and the WK here, and then have Z1, Z2. So this is basically our design, and this would be just E and U. This would be R and D, and these are passing through this blocks. So this, if you write down the matrix multiplication, you would get ws times wd. So let me just write it here, push this down. This would be ws wd times s ks st times gd, k times st times gd, and vr and vd. So that would be our closed loop from R and D to Z1 and Z2. Now we are looking for a controller K that minimizes the H infinity norm of this transfer function. Now let's try to sketch the generalized plant. Now this one looks like this. We have a G block, we have a GD block, then T, VD, and the disturbance is entering here. Then we have a reference entering here. This would be Y and this would be E. The E is going through WS to give us Z1. Then input U is coming from the controller K, and that one is also going via WK to the performance channel Z2, and the controller is as before measuring the error E. Now we can draw a block diagram around here. So we have an input R and an input D and the control input U, performance channel 1, performance channel 2, and the control measurement E. And this one is now our generalized plant. We can use this to minimize, then we can basically just run the Hinf command to get the controller key. And now the tuning knobs are WS, WK, VR and VD. As a starting point for tuning a controller, you can start with a typical shape of the inverse shaping filter WS and set WK, VR and VD to identity, and then play with these iteratively. Once you obtain the controller, analyze it, then go back to the design, change these filters, get a controller, analyze, and so on. So at this point you should really try to design the controller yourself to really observe the difficulty in obtaining a controller that satisfies all the objectives. And you can do this by modifying, creating a new design file in the design folder, and then just using this file, the name of the function that you use in the main file, to get the design and to see the analysis of your controller. And so I will say this again, I was not able to find a controller that satisfies all the design objectives. So what I tried was to design for tracking separately and then design for disturbance rejection separately. To understand why is it so difficult to find a controller that achieves both. So let's see the results for these two separate designs. So it is possible to design a controller that achieves the tracking requirements and a different controller that achieves the disturbance rejection requirements, and the step responses with these two controllers are shown here. So the dashed curves are the ones where the controller is good in disturbance rejection, that you can see by looking at the dashed curve here. So we are able to reject the disturbance pretty quickly, and the settling time requirements, which was that the output is between 0.1 for all times after 3 seconds, is satisfied. The output is less than 1 for all times, and the control input for the disturbance is between -1 and 1. But the same controller, when tested with tracking, leads to this performance. So now the same controller, when tested with tracking, leads to this high overshoot in the response for a reference step, and the control input is also slightly more than 1. So the overshoot is almost about 30%, where the requirement was to keep it below 5%. On the other hand, here you see a controller designed for good tracking, so you see almost no, so you see absolutely no overshoot unless you really zoom in, so that is clearly less than 5%. The control input is between -1 and 1 for the tracking. The disturbance rejection constraints or the objectives are not met here, as you can see that when tested with disturbance step, the output goes beyond 1, and the settling time is also far more than what is desired. Now let's look at the closed loop sensitivity plots and control sensitivity plots with these two controllers. So here you see now the 4 blocks that we designed, or that we tried to shape with the 4 tuning knobs: WS, WK, VR and VT. And here you see the two controllers, so the closed loops for the two controllers as black solid lines or dashed red lines. So the dashed red line is the controller which achieves the disturbance rejection requirements quite well, and the solid black line is the controller that achieves the tracking requirements well. So one thing that you observe is that here you see a higher peak for the disturbance rejection controller, whereas the peak is lower for the tracking controller. So what you also see is that the disturbance rejection controller almost in all the curves has some higher peaks, also leading to a higher bandwidth, and this becomes more evident when we look at the controller border plots. So now these are the two controllers designed separately for disturbance rejection and tracking, and you now clearly see that the disturbance rejection controller for almost all lower frequencies has a higher gain as compared to the tracking controller. So what is happening is that the disturbance rejection requirements require a faster controller or a high gain control action, whereas the tracking requirements require a low gain um, uh, control. You can think of it like this. So if we have a controller that is satisfying the disturbance rejection criteria, we would have a high gain in the control action that leads typically to an overshoot. Let's give an intuitive explanation of why this is happening. So let's look at the loop again. We have a controller K sending an input U to the plant G. Then we have a GD and a D. Looking through GD as a disturbance. Then we have Y. So now this GD is 100 over 10s plus 1, and that would mean if I have a step at D, the response would be something like this, and this signal, let's call it T1, that would converge very rapidly to 100. Now this G, let me have this in red. Now this G is 1 over 0.5s plus 1 squared times 200 over 10s plus 1. So this is 0.05s, so we have 2 poles at 20. So this G is a third order system, and because this T1 is very quickly moving towards 100 and we want the output Y for the disturbance rejection requirements to stay within -1 and 1, so in this case less than 1. In order to maintain these requirements, the controller must act extremely quickly to have this input cancel this T1, which is moving rapidly to 100. And because we have a third order plant with the pole at 20 here, the controller must act extremely quickly in order to raise this output of G to cancel the D1. Now on the other hand, if we have a step at R, the controller instantaneously sees an error of 1. In the case of the disturbance, the controller starts seeing an error which is growing from 0, and as the D1 is increasing, the error is increasing. So the controller does not see a spontaneous non-zero error, whereas in the case of the reference step, the controller sees a spontaneous error at time 0. And because the controller, let's say, is designed for good disturbance rejection, it has to be extremely fast. This instantaneous step at the reference causes the controller to react extremely quickly, thereby causing an overshoot. So that's one possible explanation of why it is extremely difficult to not have the overshoot when we have a reference step input, where at the same time we satisfy the disturbance rejection requirements, which are keeping the output y to -1 and 1, rejecting it quickly, and having the control input at all times between -1 and 1. So the next immediate question would be, can we solve a slightly simpler problem where this pole is faster? So for example, if the g is 1 over 0.01 s plus 1 squared, so that would mean the pole is now at 100 instead of 20, so 5 times faster g. So that would mean the controller can be slightly slower to bring this one to catch up with d1, and in this case you can see that that's indeed possible. You can check that design 3 with some slight modifications satisfies all constraints for this new g. It remains still to be seen if it is at all possible for the original g to find a controller that satisfies all constraints, and I'd like to really encourage all of you to try your best to find the tuning knobs WS, WK, VR and VD, so that you can find a controller K that does the job. If you do not find a controller K, you can then try to use any other method that you like to find still a controller that satisfies these constraints, and then it could even be a model predictive controller or a nonlinear controller. If you are able to do that, please do let me know, so that we could probably include this design in the next year exercise class. So that's it for this problem. Thanks a lot.